Ahoj. Já mám napřed jednu otázku. Je tady někdo, kdo nerozumí anglicky? No, to nevěřím. Někdo, kdo nerozumí anglicky?
Jako odborně si já.
Odborně anglicky.
Ale to vyjde
Tak jestli chceš, já budu tlumočit i to zapět,
to není potřeba. So, given that nobody actually wasn't brave enough to admit that they don't speak any English, we'll make this one the first one in English. So, hello and welcome. My name is Honza. I work for Elasticsearch, the company now called Elastic, and it is a company behind Elasticsearch. And today I'll have two talks. I'll start with the first one, which deals a little bit of theory of what search actually is, how it works, and why, and what are the necessary principles that you need to understand to be able to configure it correctly and to work with it correctly. And then in my next talk, I'll hopefully get to speak about more the Python specific sides, which is the part that I'm involved with, and how do you exactly make it work with your project in Django in Python. So first, the obvious question, like what is this search that we speak of? Imagine a problem where you actually have like a bunch of documents, and you want to search for them. So that's one way to look at it. That the search is essentially your interface to data. Whatever you do with your data, if you want to display them, if you want to analyze them, it's all search. It doesn't matter what technology you use, what the front end looks like, what the application actually does. It's safe to say that search is the interface to data. So, how do you do it when you have a bunch of documents? So imagine that you're looking for something that mentions Django. The most naive approach is you just read everything and put aside the stuff that actually mentions Django. And you can quickly imagine how that doesn't work if you, for example, had books in your library. You want to read them all every time you're looking for something that mentions Django. Or even within a book, you want to see which chapter mentions it. Or if you have a bunch of files, you just do grep-r. Just look for anything that contains Django. And actually, absolutely the same approach is if you just use icontains or ilike in a regular SQL database. That is the equivalent of these two approaches. It just reads all the data that you have in your database and looks for this one exact string. And that doesn't really scale. So please don't do this. It doesn't scale. It doesn't work. It's not good. And
I use it every day.
Yeah. No.
You should feel that.
So, this doesn't scale, it doesn't work, it will not work correctly if you have any more advanced use case. Sure, sometimes you can make it work, and sometimes you can make PHP work. Doesn't mean that it's a good idea. And also, search is really an old problem. Like, there should be a better way, right? And we probably have run into this problem sometimes before in our history. So I'm going to show you the implementation of the first search algorithm or first search data structure that is used for search. Can anybody guess how old it is?
2,500 years.
2,500 years? Any other guesses?
5,000 years.
5,000 years. You're way too optimistic. It's actually about 800 years. The first data structure that is being used to this day at that point the project was the Bible Concordance. Essentially, a bunch of monks got tired of arguing what is where in the Bible and constantly memorizing things and searching through. So they compiled a list of names and places from the Bible, and they put them aside in alphabetical orders, and they list the passages that they're mentioned in. And that is very much how we still do search today. It is a data structure that we call an inverted index. So imagine in our case we have 4 files. File 1, 2, 3, and 4.txt.
How many months are in Elasticsearch?
We do have.
Summarization.
I think we have one or two. We actually do. But we've moved past them for the most time. We realize that like CPU time is much cheaper than monk time, so we prefer that. So this is an example of an inverted index. If we have 4 files and we have 5 words, we have Django, Flask, Jest, Python, Web. So first to notice is these words are sorted. They're in alphabetical order so that we can look them up quickly. We can very easily look up Jazz just using plain old binary search. Nothing too exciting. And then the list of files, and for each line we have essentially the list of files where this word actually occurs. And again, that is sorted. So what then happens if we actually do a search? If you're looking for something that mentions both Python and Django, super simple. We locate Django, we locate Python through the binary search, we locate the individual lines, and then we just walk the list. And because both of the lists are sorted, we just merge them, and whenever we find a file that's both in the list for Python and in the list for Django, that is our result. So it is very easy. It is a very efficient operation. We're essentially just merging sorted lists. So what then happens if we're looking if we want to look for a phrase, not just a simple word, but individual phrase? That is actually doable with the inverted index. We just need to do one thing. We need to enhance the data that we store inside the index. And for each of the words and each of the files, we not only have to store that it is there, but we also store on which positions in the file this word occurs. So in this case, it's the 5th word. Here is the 2nd and 4th, obviously starting from 0. And this then allows us that if we're looking for a phrase, Python web, we again look up the Python and web, we walk through the list, but we only merge those documents where the positions are offset by 1. So here Python is the 2nd word, and web is the 3rd word, which actually matches the phrase, because it means that web follows Python. File 3, it contains both Python and web, but not the phrase Python web. So this is how phrase queries work. And you can immediately see that we are not only limited to the distance of 1. For example, we can say that the distance should be less than 3. So we can allow for some arbitrary words to be in between those two. Or we want to just find a passage that deals with both of them. And we can be more granular than this. So we can enhance the data that we store in the inverted index and thus get much better results, and also be able to use other types of queries, not just the simple, straightforward ones. So again, it's all just merging sorted lists, and the fun part about it is you don't actually care where the list came from. So imagine that you have a book. Let's say you have the Bible, and at the end you have 2 indices. You have an index for places, an index for persons. And then when you want to see if there is a passage that mentions Jesus in America, you can quickly look at those two things in their 2 respective indices, and then merge those 2 lists of pages, and immediately find out that Mormons would be disappointed, but yeah, Jesus was never in America. I'm sorry, that was a fairly localized joke. This means that we can use different indices at the same time. We're not like other data stores where we are limited to typically 1 index per collection or table per query. We can use all of the indices at the same time, and there is no such a thing as full table scan, where you have a full text search engine. So, the only trick to an inverted index is how to actually build it. Once you have it built, it's super easy and everything is fine. But I still haven't shown you anything that that you couldn't do with a more traditional data store like SQL or anything like that. Sort of the full textness of it. That it will match even words in different shape or form, in different declination, with different endings and everything. And that part that magic happens when you're actually building the inverted index. So let's say that we have a sentence here that we will index. First thing that we need to do is we need to split it into words so that we can build the inverted index. And during this splitting, it's not just we just split it into words, because you can see the results here, and it doesn't actually match. For example, in the text we have encourages. In the index, we'll just index encourage. And that is because ES at the end is just an artifact of the grammar. It has nothing to do with the word. And if someone searches for framework encouraging, they should be able to find this document. So that's why we strip out all of these unnecessary stuff. This process is called stemming. We're looking for the stem of the word, for the core of the word that uniquely identifies this word. So that's this part. You can also notice that all of the words are lowercase, because obviously if you search for something in uppercase or lowercase, you should always find this document. Also, some of the words.
I'm just super curious. Sorry for our foreign guests. Do you know the Czech words for stemming and stuff? It's just like when you mention something.
So it's just saying stemming is we're looking for kozen slova.
Sure.
So. But there are actually two different processes. There's stemming and there's lemmatization.
That was my question.
Yeah, so those are two different processes.
Stemming or lemmatization?
Yeah, I'm describing stemming. Lemmatization is the next video, maybe. Okay. So the other thing that you can notice is everything is lowercase, and also I skipped some words. I don't care about indexing is, or a, or and. Those words are useless. They'll most likely, when we're dealing with English text, they'll most likely be in every single document. So the information that we found then means nothing. So I'm just skipping them. Those are called the stop words. Those are words that are way too common, that they don't bring anything to the table. And then there are some other things. For example, here, it encourages rapid development, which is fine if you have a very big vocabulary. But if you're a simple person like me, I just want to find something that allows me to develop fast, not rapidly. So instead of just indexing rapid, I index all the synonyms as well. Because fast is a synonym for rapid, and fast is way more common. Instead of just indexing rapid, I index rapid and fast. So when I search for fast development or rapid development, I'll always find this document. So this entire process that I just described, it's called the text analysis. And it happens at index time. When you put something into Elasticsearch or Solr or any other full text search engine, this is what happens. And that is also.
And it happens at both levels, in Lucene or in higher levels?
Depends which technology you're talking about. It depends through all the layers. Some of it happens at Elasticsearch level, some of it on Lucene. Mostly on Lucene though. And because it happens at index time, that also means that you can never change it. Once you have the data indexed, once you have the data in your data store, you cannot change any of that. And if you do, you have to re-index all your data. So this is how to actually perform the analysis, and this is just some of the steps that we did. We split into individual tokens into words. We dropped the stop words. We did lowercase. We did stemming. We did synonyms. There are so many other steps that we could take. For example, there are stemmers out there that don't rely on the written form, but they try to identify the phonetic quality, so how it would be pronounced. So that is much more useful for other languages. English is very, very simple. If you have different languages, it might be better to try to essentially analyze the sound of the word than the spelling of the word. So it all happens at index time, and the important part is when you search, when you actually send in your query, the same process needs to be applied for the query. Because again, if you're searching for encouraging and you've indexed encouragement, it won't help if you just apply this entire process to what you have indexed. Then you have to get encouraged, but it will still not match the input. So if you have encouragement and you do it into encourage and encouraging and again to encourage, then it will match. So only by applying this process to both the query and the document itself can this process actually work. So last thing that I'll talk about before handing it over is relevancy, because that's very important for a full-text search engine. Because you can do filtering in any other data store, and it wouldn't be too hard to actually construct all this in any other data store. What we have and what other don't is we tell you not only which document matched, but how well did they match your query. So we can sort them that this is a good match and this is a bad match. So how does this thing actually work? Well, it's very simple. No, it actually is. The core of the formula is this part. Is a TF-IDF based formula. TF stands for term frequency, and IDF for inverse document frequency, which are a super fancy word for saying how many times the word is in this particular document compared to how rare or common this word is overall. So if you have a word that is super common and you find it twice in this one index, it doesn't really mean anything. But if you have a word that's only contained in 1% of your document and you find it twice, that is actually something that means a lot. And that is actually what this number signifies, what this number will result in. Then we have some other gibberish around. For example, we try to allow for the length of the field. So if you find a word in a short field, it obviously means more just through the nature of statistics than if you find the very same word in a very long field. So that's this part. And then you might even assume, have some arbitrary weight assigned to certain fields or certain terms that will again mess with this formula a little bit. That's the part at the end, the boost part. This part can be ignored apparently, so we'll not go into it. And by applying this formula, we can actually say which document matched better. And we can apply this formula because we have all this information in the inverted index. We obviously know how many times the word is in this document, and we also know how many documents this word is involved in, because it's the length of the list from the beginning. That's the length of the row from the inverted index, as I showed you. So this is actually how relevancy works. And this is actually what it means. So as I said, there's several fields several aspects that go into computing the overall score. And these are it. The rareness of the field and the rareness of the term, the number of occurrences in the field, and the length of the field. And that is it.
Sorry, what is a field?
A field? It's anything that you index. So imagine that you have a document that has fields. You can have. It depends on your document. So typically, what you work with is like JSON documents. So any value. So imagine that you have a title field and body field and stuff like that. So that would be your field.
It's basically a subset of the document.
Pretty much, yes.
Thank you.
Okay, so if you just apply those rules, you don't. It doesn't have to be Elasticsearch. It doesn't have to be Solar. Everything works. Everything works pretty much like this. I've even tried and implemented this in pure Python, just using dictionaries and lists, and it actually works fairly nice, and you can get very good results. This technology is not rocket science. It has been developed by monks in 1230. It is not so difficult.
So what you just described, the theory behind that, how much different would be the technology for web context? Like the question. Well, I mean like Google.
I actually know a question. When it's so easy to build full text search engine, how is it possible that Shazam doesn't have full text engine after 15 years of...
You have to ask someone who does that, not me. This part is, it uses the same principle. The difference in how, for example, Google or Shazam or other would, the difference is how you compute the relevancy. Because they have much more information about the documents. For them, documents means websites, web pages. And they actually assign weight and importance, page rank, anyone, to the individual sites and documents. So it's not about how well they match the query. That is important but not crucial. The crucial part is how good a site it is. Also, they often don't index what's on the site, but also what points to the site. So it's even more stuff is happening at index time when they actually crawl the web and collect all these information.
Mostly user experience to it. So if they display something on a page 1 million times and they calculate that people click on the third link, they promote the third link on the page.
Oh yeah, totally.
Yeah. Okay. Last question. Going once. Yeah.
Where do you take the thesaurus for the set of synonyms?
You have to configure them manually. Okay. So that was it from me for the first part. And now. 10-minute beer break.
Hey,
Or
Ben has a question. The synonyms. Is there context?
you can have multi-word synonyms.
What I mean, so in the example that you showed where you had Python, you might, if somebody was talking about the snake, it would be different to if they were talking about.
So typically there is it really depends how you've implemented the analysis process. If we're talking about Elasticsearch in particular, there is no context.
Right.
The only thing that you can have is you can have multi-word synonyms. So it doesn't have to be one word for other word, but it can be a phrase. But other than that, no, you would have to implement it yourself.
Does anybody do that?
Yes, people do. But also, most people actually know what their data set is about. It's rare that you have a mixed data set, that you would have both text talking about snakes and programming. It happens, but not that often. So this is not as widespread problem as one might think.
Okay.
Cool. So,
Oh yeah, let's digest a little bit. 5-10 minutes.
5-10 minutes.